Hi, in this video we will learn about new objects in M space called hyperplanes. Hyperplanes are generalizations of planes, but instead of in R3 in general RM space. So let's just start recalling what was the key points about planes on in R3. So planes in R3. First of all, they were defined or determined by two things. So determined by a normal vector, a non-zero vector, and a point. Well, they can be described by a linear equation. Remember that linear equation, which was, well, in this case, ax plus by plus cz equals to d if you write it in the standard form, and its dimension of a plane is 2. Well, now we want to have a generalization for these guys in RM. We want to see what kind of objects are determined by a normal vector and a point P. Are they going to be given by a linear equation? Well, linear equation in this case will be, we have a1, a constant, times the first coordinate, another constant times second coordinate, and goes up to m constant times xm equal to another constant c. And well, so far that's what we have. It is determined, and yes, it will be described by a linear equation. And the nice thing is that the dimension of those objects are going to be 1 less than the dimension of the whole space. So this was supposed to be in RM. So in RM, yes, we have an object which is determined by two things, a normal vector, a point. It is described by a linear equation, and its dimension is 1 less than the dimension of the space, and it is called hyperplane. Well, that being said, as basics of what is a hyperplane, now we can see how to write an equation for a hyperplane. So if a point on a hyperplane, a point P on a hyperplane, and a normal vector n is given, then we can write two forms of equations. One is called point normal, exactly same as planes in R3, which is of the form, well, you have n, you have dot product x minus p equals to 0. And then we have, standard form, which you by expanding n dot p, n dot x equals to n dot p, we find that expansion, and it is of this form: n1 times x1 plus n2 times x2, and then goes up to nm times xm equals to some constant. So this is by expanding, by performing dot product. So you get that equation. Very similar to plane in R3. Well, knowing these things, let's just do one example. Find equations in both forms for a hyperplane in R5 through point 1, 0, negative 3, 2, 1, and with normal vector negative 1, 5, negative 4, 3, and 2. Very nice. So we have 0.1, 0, negative 3, 2, 1, and vector, normal vector, negative 1, 5, negative 4, 3, 2. Then we can write point normal form which is n here, negative 1, 5, negative 4, 3, 2 dot. X here is the coordinate variable, the vector. So it's going to have m here, 5 variables. We usually index them like this. Minus p is 1, 0, negative 3, 2, 1. This equals to 0. That is the point normal form. How about the standard form? Well, let me just write it here. N dot x equals to n dot p is going to give us that equation. So negative 5, negative 4, 3, 2 dot x1, x2, x3, x4, and x5 equals negative 1, 5, negative 4, 3, 2 dot 1, 0, negative 3, 2, and 1. Well, let's just simplify this. Multiply corresponding components and add them. Plus 3 times 2 plus 2 times 1. This is negative 1 plus 0 plus 12 plus 6 plus 2. And when you add them, you get 19. So this gives us minus x1 plus 5x2 minus 4x3. I'm just performing this dot product. Plus 3x4 and then 2x5 is equal to 19. So that is the standard form. This is point normal form. Again, you have to know what does hyperplane geometrically mean, what kind of information you need to write an equation, and what kind of forms we have for hyperplanes in M space.